Warm-up for lesson 7-1, function versus one-to-one function. In our first example, we have a function, but its inverse is not a function. Remember that the horizontal line test on f of x will indicate whether the inverse is a function. Now let's take a look at f of x equal to x to the third power. Notice that the red graph does pass the horizontal line test, and we can see by the inverse it is going to be a function. So the horizontal line test is a test for one-to-one. Let's take a look at continuous versus non-continuous. This is not continuous because there is a break in the graph. This is continuous because there's no breaks. This is not continuous because we can see there's a break. And over here, polynomials are continuous functions. Increasing, decreasing, or none. Notice that increasing is from -3 to 0 and from 3 to infinity, and decreasing is -infinity to -3 and 0 to 3. This is an increasing function from here to here and here to here, and we say it's constant. In other words, it's not increasing nor decreasing in this interval. For our parabola, it's increasing from -infinity up to x equal to 4, and it's decreasing, the y's are going down from 4 to infinity. Lesson 7-1, graphing exponential functions. Objective, graph an exponential growth function, graph an exponential decay function. Okay, let's take a look at different parent functions that we've worked with: constant, linear, absolute value, quadratic, square root, cubic, and just polynomials in general. This function that we're going to be talking about is called exponential. And exponential are going to be growth or decay functions. Now, this line is a growth function, it's growing, but exponentials increase a lot faster. Let's take a look at what an exponential function looks like. This is a polynomial function right here, x to the 5th power. The exponential function is 5 to the x. Notice that the exponent is now the variable and the base is the constant number. Okay, so 2 to the x, 3 to the x, all of these represent exponential functions. And in particular, we want to talk about growth functions. And in order for an exponential function to have this growth feature right here, the b has to be greater than 1. So notice that all these bases are greater than 1. Even 10 to over 3 is bigger than 1. Now, notice that the domain is all real numbers, but the range is only positive real numbers. Notice it doesn't dip down underneath the x-axis. Also, when you substitute 0 into the function, b to the 0 is equal to 1. So this will always be the y-intercept. The end behavior is as x goes to infinity, as x gets bigger, y gets bigger. As x gets smaller, notice that the y continues to be at 0. When this happens, when f of x follows a number like 0, 1, 2, or something like that, we call that an asymptote. So we say y equal to 0, the x-axis is an asymptote. And so the asymptote says x-axis, or we write the equation for the x-axis. Okay, let's take a look at an example, and let's do another growth function. How do I know it's growth? Well, because there's the 3 right here. And let me go ahead and substitute some values. I'm going to do 3 to the 0 power. 3 to the 0 power is 1, so this is 1. 3 to the 1 is 3. 3 to the 2 is 9. So we're going to plot these points: 0, 1, 1, 3, and then 2, 9. Now let's substitute 3 to the -1 power, and remember that means 1/3, and 3 to the -2 power, and that means 1/3 to the 2nd, which is also the same thing as 1/9. And notice when we graph at -1, we graph 1/3 and 1/9, and notice that we never get negative numbers, but they get smaller and smaller. So the domain is all real numbers. The range is from 0 to infinity. Now notice that I put a parenthesis here, so it's not including 0. And then our end behavior, as x goes to -infinity, f of x approaches 0. As x goes to infinity, y approaches infinity here. So whenever this happens, as n behavior becomes a constant, we know we have an asymptote, and that'll be y equal to 0, which is also the x-axis. All right, let's take a look at another one, and this time we'll do 4 to the 0 power, that's going to be 1. 4 to the negative 1 power is 1/4. 4 to the 1 power is 4. So let's go ahead and graph that. And then 1, 1, 2, 3, 4, negative 1, 1/4, and our graph will look something like this. Try not to have it cross the x-axis here. So the range is negative infinity to infinity. Range is 0 to infinity. Remember, do not put a bracket there. In behavior, as it goes to negative infinity, that's 0. As it goes to positive infinity, it'll be positive infinity. And because of this, we have asymptotic behavior, which is y is equal to 0. Your turn. Stop the screencast and see if you can pick out the function. And here's the answer. I went ahead and substituted some points here so that I could find the graph and match it up. Here are some words that we're going to be covering: exponential function, exponential growth, asymptote, growth factor, exponential decay, decay factor. All right, let's move into a decay function. It still has an exponential form. It's 1/2 to the x power, 1/3 to the x power, because we have to have our base be between 0 and 1. And this is the same thing as 1/4 to the x power. And this is the same as, I should put it down here, as 1/5 to the x power, which is the same thing as 1/5 to the x power. So all of these are examples of decay. Okay, in decay we're going to have a continuous one-to-one. Notice it's decreasing. That's where we get the word decay. It's going to be all real numbers, positive real numbers, and the x-axis is going to be asymptote, and we're still going to have this asymptotic behavior here. All right, let's go ahead and practice. I'm going to do 1/3 to the 0 power, and that's going to be 1. And then I'm going to do 1/3 to the 1 power, and that's going to be 1/3. And 1/3 to the second power, and that's going to be 1/9. Now let's do 1/3 to the negative 1 power. Now there's a lot of ways we can look at this. We can look at this as 3 to the negative 1 power, to the negative 1 power, pow, multiply me now, and that's going to be a 3. Or you could just think this means reciprocal, and the reciprocal of 1/3 is 3. So this is going to be 1/3 to the negative 2 power, and that's the same thing as 3 to the second. Remember, that's a reciprocal relationship, and that's going to be 9. And this is the graph right here. So the domain is going to be all real numbers. You can put any number in there. Range is going to be 0 to infinity, not including 0. And behavior, as x approaches negative infinity, f of x is getting bigger. So as it goes this way, it wants to go up. But as it goes this way, it wants to stay at 0. This is going to tell us that we have an asymptote, and that's going to be y equal to 0, or the x-axis. Okay, let's go ahead and graph another one. This is 1/5. So 1/5 to the 0 power is 1. 1/5, 1/25. And then this is 1/5 to the negative 1, which is reciprocal, 5. And then this will be 25. So negative 1 to 1, 2, 3, 4, 5. And then 1. And then we go down. So the graph's going to look like this. It's a decreasing function like this. And it should be going out like this a little bit more. Okay, so the domain is all real numbers. Range 0 to infinity. In behavior, as x goes to negative infinity, it wants to go up. And as it goes to positive infinity, it wants to stay at 0. This tells me we have an asymptote. Y is equal to 0. Your turn. And here's the answer. I went ahead and graphed a couple of points to see where I was at. Okay, so exponential function general equation. We call this the initial value. We haven't been having one of these before. We've just been having the base, or what we call the growth or decay factor, and we've had the exponent. So we just have this part right here. I want to introduce this initial value. Okay, so in this problem, the initial value is going to be 100. And what is it, a growth or decay? Well, this number is between 0 and 1, so it's a decay. So it's going to have kind of this look right here. Now, this is my initial value, and that's 40. And this is going to be a growth. How do I know it? Because this number is bigger than 1, and so it's going to have like this characteristic. My initial value will be 10,000. And this is going to be a growth. How do I know? This number is bigger than 1, so it's going to have this look. This is an initial value is going to be 50, and this is a decay. How do I know it's a decay? This number right here, the base or the factor is less than 1, so it's going to have this kind of a look. All right, so let's go ahead and try some of these problems. A, what kind of, is that exponential growth or decay? Well, it's actually a growth. Notice how it's getting bigger, going as x goes to infinity, it's going up. Now over here, this is a exponential decay. How do I know? Because as x gets bigger, it just stays the same. Okay, over here, I'm not looking at the graph, but I can see that the factor right here is bigger than 1, so I know it's a growth. And over here, I know that this number is between 0 and 1, so it must be a decay. All right, so I'm looking at this equation. I want to identify whether it's growth or decay, and it's going to be growth, and its factor is 1.23. The initial value is going to be 1. How do I know it's 1? Because y equal to a times b to the x power. This a isn't part of the exponential part, so I know the initial value is 1. The growth rate is this number bigger than 1, so 0.23 is what we call the growth rate. This is the part that makes it over 1, so that's what we call growth rate. Let's talk about shifts, transformations of parent functions. You know that in the parabola, the h and the k and the a said something about how we change the parent function. Now, h, it tells you how much you're going to shift to the right. And if it's plus h, then that means it's shifting to the left. Plus k means it's shifting up, minus k is shifting down. If a is negative, there's a reflection over the x-axis. And if a is greater than 1, it's a stretch, it's a vertical stretch. And if a is less than 1, it's a vertical shrink. So that same kind of thing happens with exponential functions. So h will be a horizontal translation. If h is to the right, if h is a positive number, this part is positive right here. And absolute value is left if h is negative. So this part right here is negative. Now, k is the vertical translation. And if a is negative, it's going to be a reflection. And if a is greater than 1, it's a stretch. If a is between 0 and 1, it's a compression, or we call shrink. So let's take a look at this problem. Now this is the parent function right here, so I went ahead and graphed the parent function. This is actually a vertical shift, so I'm going to take this, all the y's, and I'm just going to subtract 2. And you notice that I went ahead and just graphed it here, so all I have to do is connect the dots right here. And that's what it looks like. And you can see it looks like it shifted down 2 units. Every point is shifted down 2 units, including the asymptote. Look at that. Let's take a look at this one. Now this is going to be a horizontal shift. And in this case, because 1 is positive after the minus sign, it's going to be shifted to the right. So you're going to add 1 to each one of these. So again, I went ahead and added 1, and I graphed all these points. And then I'm going to connect the dots, and you can see every point has been shifted over 1 unit. All right, your turn. Decide what you're going to do. Work with the parent function. And here's the answer. So what I did is I just shifted down, which means take all your y's and subtract 4. Try again. And here's the answer. In this case, there were two things happening. I had a horizontal shift to the right, so I added 2 to all my x's, and this was a vertical shift up, so I added 3 to all my y's. I found the graph that had all these points, and I noticed they're right here. Another dead giveaway is that the asymptote was shifted up 3 units. So that's another way to avoid these answers that didn't make sense, and this was a shifting of over 4, so we can do that as well. Okay, here's a more complex problem. So I went and took my parent function, which is this, and what I'm going to do is this tells me to add 1 to all my x's. This tells me to multiply by -4, because that's that factor that we're multiplying by, but then this is a vertical shift, so +2. So I'm going to actually plot all these points. So this is going to be the point 1, and then this is going to be -2. So 1, -2, and then this point is going to be 2, and this will be 0, 2, 0. And then this point is going to be 3, and this is 3. This looks like 1. So I'm going to have 3, 1, and now I can go ahead and graph my curve. And here is the curve right here as well. Here's how I did it, and here is what the answer looks like. Okay, your turn. And here's the answer. Again, go ahead and draw a table, and this means to shift to the right 2 units. This means multiply the y by -6 and then subtract 3 on that. Okay, here is another exponential application. It's percent increase or percent decrease. And it looks something like this, where if we add 1, if we add something, 1 plus something, it's going to be a growth. If we subtract from 1, it's going to be a decay. So let's take a look at a problem like this. In the internet, there were these many people worldwide using the internet. So this is going to be our initial condition. So it's going to be our A, what we started off with. At that time, the number of users was growing by 19.5%. Remember, this changes, when you change it to a decimal, it changes to this. So this is what we're going to be, our growth rate. This is what we're adding to the 1 to make this number bigger than 1. So let's take a look at the answer, what it looks like. They want us to write the equation, and so we're going to take this percent number, we're going to add it here, and this is going to be a number bigger than 1. Here's our initial condition, and here's our t, and here's our graph of that. One more, this is a decay. In this case, the pressure of the air is this, so this is going to be our initial condition, and we're going to be decreasing by 20%. Remember that 20% in a decimal is 0.2, so we're going to be subtracting 0.2, which is going to make this less than 1. Okay, and this is what the answer looks like. We're going to, again, here's our initial condition. We're going to subtract. So when we subtract, we're going to get a number less than 1, and this is what the decay function is going to look like.